So this lesson is IB Chapter 13, E and F. First, E is the shortest distance from a line to a point. A ship R sails through point A in the direction B and continues past a port P. At what time is the ship closest to the port? So, from your geometry, you probably remember that the shortest distance from a point to a line is along the perpendicular. Oh, whatever. So, it's going to be that distance that's along that line segment I just drew. And using vectors, the way we would know that, well, we could think of this as vector PR. The way that we would know that PR and AR are perpendicular is by their dot product equaling 0. So it'll be closest when direction vector B dotted with vector PR is equal to 0. And by the way, R is called the foot of the perpendicular from P to the line. So R is on the line. R is this point here. And that's kind of cool. I'd never heard of that before. Example 10. A line has a vector equation. Oh, yeah, since I wasn't feeling well, I just kind of threw these together really quick. Let's move these up to where they should be. It's gonna, sorry about this, it's all confuzzled. That equal shouldn't be there. You know what? I'm just, okay, this should be, 3 should be up there, -1 should be there. Let's just ignore that. Okay. I was in the process of making these slides, and then I'm just, since I'm not feeling well, I'm just gonna do them from scratch here. To use the element of the reals. Okay, so they give us this vector equation, and it says, it's also going to say let P be the 0.5, -1, and they want to find the shortest distance from P to the line. Okay, so that's the problem. And this is in 2 dimensions. I like to draw pictures. It just helps me think. It helps me set it up. So I've got the 0.5, -1. 1, 2, 3, 4, 5, down 1 right here. And the line, I'm just going to sketch it real quick too, just helpful. It starts at 1 over 1 up 2, and its direction vector is to the right 3, 1, 2, 3, and down 1. So there's the line. And at some point R, which by the way is not necessarily this point right here, in fact it's probably more like over here, that's the R. So at some point R, there'll be, it'll cause the shortest distance here. And so we need to find that point, or do we? Actually, what we want to do, since this is such an important point here, is we want to find its coordinates. So we can get that. Oh, we know its coordinates from the vector equation. For some, it's going to be 1 plus, you can think of it as, so R will have coordinates from the vector equation. We know it's going to be, the x will be 1 plus 3t, and the y will be 2 plus -1t. And then, because we're dealing with vectors, what we can do, we already have the equation for the orange line there in vector equation. Well, let's come up with a vector equation for the vector PR. And then once we have that, we could find the dot product and that'll tell us the time. And once we have the time, we can find r. And once we have r, we can find the shortest distance. So we need an equation for vector PR. And that's going to be r, the coordinates r minus the coordinates at p. So we already found the coordinates r. We got those from the vector equation, since r is on the line that was given. So we're going to have, oops, let's make these like so. We're going to have, since we're going from p to r, we're going to have r, which is 1 plus 3t minus the coordinates of p, and then 2 I'm going to write that as minus t. Whoopsie. 2 minus t minus negative 1, so plus 1. So that's going to be negative 4 plus 3t and 3 minus t. That's the vector equation for vector PR, and then we have the vector equation for the line, which is up on the top there. And so now, since we want to know when they're perpendicular, we can do the dot product. I'm going to write the top one, so this is, I'm familiar with this notation, so that's how I'm going to write the other one also. I think this was vector, let's just call that A, so I have a way to write it. That's going to be 1 plus 3t and, oh, you know what though? We don't need the vector equation. We only need its direction vector, so never mind all that. Let's make it easy on ourselves. The direction vector is 3, negative 1. Okay, so we can dot those two together. Negative 4 plus 3t times 3 plus 3 minus t times negative 1 will equal 0 because they are perpendicular. And let's see here, so we're going to get negative 12 plus 9t minus 3 plus t equals 0. So that's negative, coming over here, negative 15 plus 10t equals 0. Add the 15 across, divide by 10, divide by 5, and we get t equals 3 halves. Okay, it wants the shortest distance from P to the line. So, what we could do, the shortest distance from, so there's two ways you can do this now. There's the non-vector way, which would be to plug 3 halves into, right up here, let's go to, right up here you have the coordinates for r. And you could plug 3 halves in for t, and you could get the actual coordinates for r, and then you could use the distance formula. That's one way to do it. The other way is using vectors. Let's do it that way since that's what we're studying. We could find the vector PR, because we have the vector equation here. And then once we have that vector, we can find its magnitude, which will be its length. So let's do it that way. Oh, I need more room. Okay, well, I'm just going to do it in purple. So I'm going to be plugging in 3 halves. So I'm going to have negative 4 plus 3 times 3 halves is 9 halves. And then I'm going to do 3 minus 3 halves. So let's see, that's going to be a half. And that's going to be 6 minus 3. That's going to be 2 over 2. That's going to be 1. Oh, is that right? I'm going to make sure I do it right. That should, oh, 3 minus 3 halves is 3 halves. That's why I'm not 2 times 6. 6 minus 3 is 3 halves. Okay, that makes more sense. Sorry. Ah, it's too big. I knew that wasn't right. Okay, so that was 1 half, right? 2, that's 8, 1 half, and that's going to be 3 halves. So that's the vector, P to R, PR vector. Now all we have to do is find the magnitude of that, because that'll be its length. So the magnitude is the square root of 1 half squared plus 3/2 squared. So that's going to be 1/4 plus 9/4, which is 10/4. Working up here. Sorry for the craziness. And then the square root top and bottom, so you get root 10 over 2. And that is the length. And then there's no units, so don't have to worry about that. Alright, so now example 11 is, it says on the map shown, so we have to draw a picture. O is down there in that dip. There's a point R here, X, Y. Point P going, whoopsie, it's supposed to be a point right here. Okay. It does give us the direction vector, which is 3, 4. And this is the origin. This is 10, 2. This is -8, 3. Distances are in kilometers. Ship R is moving in the direction vector 3, 4 there. Oh, and it's moving at 10 kilometers per hour. So this is example 11. It's moving at 10 kilometers per hour. A is to write an expression for the position of the ship in terms of t. So we want the position vector. And notice on this one, it is moving at a constant velocity. 10, this is our velocity here. So, well, it's actually the speed, I should say. That's the speed. The velocity is a vector, which we're going to have to figure out. So we're going to use the position vector formula that we've been working with, which is, oh gosh, is it P? Drats, I think it's just P. Is the original position plus time times the velocity vector. All right. Well, we know the initial position is -8, 3. So we'll have x, y equals -8, 3. That's given. And then t. Oh, and t is in hours, I believe. Yeah, t is the number of hours. T is number of hours. Okay, so, sorry to think about this. You can't use, so the velocity vector, that's the problem with this problem. That's the tricky part. It does give us a direction vector of 3, 4, but this is the problem where you can't use 3, 4. Whereas on those earlier problems, we were able to use it as our velocity vector, and on this one, we're not able to use it. And I'm not exactly sure why. So I will try to figure that out. For now, we're just going to trust it. For one thing, you might notice the direction vector of 3, 4, what would its speed be? Let's find that, because this will shed a lot of light. This actually sheds light on why you can't use it as our velocity vector. The speed would be the magnitude of the vector 3, 4, which using the 3, 4, 5 triangle, we would know it would be 5. But just to show you, that would be 3 squared plus 4 squared, root 25 or 5 kilometers per hour. And so that's just coming from the direction vector. But it tells us it's really moving at 10 kilometers per hour. Well, that happens to be twice the speed of this direction vector, right? So this one, they set this up nicely for us. All we need to do then is multiply the direction vector by 2. So 6 and 8. And you can check the math. Oh, sorry. I'm using the Pythagorean triples, the 6, 8, 10 triangle. Okay, so we've answered question number 1. There is another way to do these, to find this velocity vector. It involves the unit vectors that you learned in pre-calc, because if you find the unit vector for 3, 4, the unit vector by definition has a magnitude of 1, and then you can multiply that unit vector by 10. And maybe I should show you that in case you come across a problem that's not as obvious as this one. So the